Now we're going to look at the derivation for the capacitance equation for the parallel plate capacitor. Now, the first couple of steps are steps we are very familiar with. We've seen them before. So our first step is to get an expression for the electric field for the capacitor we're talking about between the plates, between the positive and negative plate. So, as you recall, I hope, we use a Gaussian surface. Cylinder stood upright, punching a hole through the surface. Our Q enclosed represents a cross-sectional area equivalent to the area cap. That we have one area cap inside that will see electric flux for the electric field passing through. There is no electric field outside of the plates because, if you recall, our Q enclosed would be 0 if we extended the Gaussian surface. We're also ignoring all of these edge effects, so we're not going to look at any of that non-uniformities. We're looking at what we always did, the constant electric field between the plates of the capacitor. When we do that, we get flux only through that green cap in the middle, so that's what we have here. Our Q enclosed comes from the fact that sigma, just to remind you, the charge density, sigma is charge per area, so Q enclosed is sigma times area, so that's where my sigma A comes from. We get our very nice cancellation here. The area cancels, and we have our result that I hope we are all very familiar with, the fact that the electric field is a constant. It equals sigma on epsilon naught between the plates. Well, all we are going to do now is go to our expression from our potential chapter, our last chapter, and take that electric field value, right, the sigma on epsilon naught, and plug it in here. So we're going to plug it into that integral. Now, the most important thing in terms of our delta V integral, which will be important relative to your getting your pluses and minuses correct anyway, is to make sure you are integrating from the negative plate to the positive plate. So please get this into your notes. And you want to think then about what is actually going on mechanically when you are going to integrate from the negative plate to the positive plate. That's like taking a positive charge and pushing it backwards against the electric field to the top plate. So I'll talk about the math in a moment, but just to give you a visualization of what we're talking about, if we take a positive charge down here near, right at the bottom plate, so down here at the negative plate, and we are going to mechanically, physically think of pushing it up to the top plate. So this is going to be our dr in this case. That's our differential increment that we are moving it over. So our electric field is down. So there's our 180 degrees between the E and the dr when we take our dot product. And the reason we do this is because the energy required to do this mechanically will be the equivalent energy that it takes the battery to take a positive charge and put it onto the top plate. What the battery has to do in overcoming the back voltage is overcome this type of resistance that we're talking about mechanically. It's a mathematical equivalent. So when we do that, we get a very nice result here, right? The electric field is sigma on epsilon naught, so E is constant, so it's actually going to come out of the integral. We're left with the integral of dr from 0 to d is d. We've already talked about why we get the cosine of 180, so that goes along with this negative to give us our positive sigma d on epsilon naught. And actually, we're going to go back and put the q back in. Anytime we do these derivations for capacitance, we want to put our voltage back in terms of the q's, because what we are going to do is take this voltage value and plug it in for the V in our definition for capacitance. Capacitance in general, whether it's the parallel plate capacitor, cylindrical capacitor, spherical capacitor, capacitance always equals Q on V. We can see we get the Q's cancel out nicely, and we just rearrange it algebraically to get epsilon naught A over D, and the only addition that I put in was the addition of the kappa. That's our dielectric constant that we've talked about. And if you recall, the dielectric constant for vacuum is 1, but for any other material, kappa will be greater than 1. So what's going to change the capacitance of our parallel plate capacitor? Well, area, certainly, if we physically, literally make a larger capacitance. The separation between the plates, so this we had alluded to, but we see how it comes out in our equation as well. The distance between the plates gets smaller, the capacitance gets bigger. And if we replace the material between the plates with a better insulating material, a higher dielectric constant, then we will increase the capacitance. And definitely make sure you get into your notes this last little bit here, because as we have said before, but it's really important, C does not change unless you change the actual capacitor. You swap it out. So we've changed the kappa, the A, or the D, right? If Q changes, C does not change. If Q changes, it just means V changed. So if Q and V change, right, they'll change together, but C remains constant unless we literally swap the capacitor out. So there's the derivation for the parallel plate capacitor. You're going to do the derivations for the cylindrical, spherical capacitors. We'll talk about those in our upcoming videos.